Here's another example. We have two disks rotating around the same axis that passes through both of their centers perpendicular to the disk. So this is hard to picture with just words, but basically what it's saying is that there's a disk, and there's another disk kind of aligned on top of it, and they're both spinning around. So we've got two disks, they're brought into contact, and they begin to rotate together. So the only torques being exerted on them are friction from the other disk. So angular momentum is going to be conserved. So our initial angular momentum equals final angular momentum. And this is just like, this is the rotational equivalent of a perfectly inelastic collision. When our mass is stuck together, it's called a perfectly inelastic collision. Same thing, rotational. This is a perfectly inelastic rotational collision. Initial angular momentum, disk. The moment of inertia of a disk is 1/2 mr squared. With all these numbers, I'm not going to write out variables. So disk A, you've got 1/2 mr squared, so that's I, times omega, angular velocity, 5.5, plus disk B, 1/2 mr squared times omega, which is negative 3.6. The z, this is the z hat. Or you could also say the k. It's in the k direction, vertical direction. And that's equal to final angular momentum. Since they move together, then we have their total moment of inertia, which is 1/2 mr squared for each of them, times omega final. And then we can calculate that final angular velocity, 0.5 times 1 times 1.3 squared times negative 3.6. I did 1/2 times 2 and got 1, so I ignored that part. Divided by 0.8 squared plus 0.5 times 1.3 squared. So we get that their final angular velocity is about 0.32 radians per second, and that is in the z hat direction. It came out positive, so we know it's in the positive z direction. How much energy is lost? Well, again, it's initial kinetic energy minus final kinetic energy. Initial kinetic energy is 1/2 I omega squared, and that's equal to 1/2 I total times omega final squared. So we've got 1/2 times 2 times 0.8 squared times 5.5 squared. I don't know why I put the big parentheses here. Plus 1/2 times 1/2 times 1 times 1.3 squared times 3.6 squared. And that's equal to 1/2 total angular momentum, which is 1/2 times 2 times 0.8 squared plus 1/2 times 1 times 1.3 squared times omega final, which we just established is 0.32 something something squared. Whew, just about ran out of space there. Sorry about that. Oh, not equals. What am I doing? That's k naught. That's k final. So not equals minus. So 0.5 times 0.5 times 2 times 0.8 squared times 5.5 squared plus 0.5 times 0.5 times 1 times 1.3 squared times 3.6 squared minus 0.5 times 0.5 times 2 times 0.8 squared plus 0.5 times 1 times 1.3 squared, close parentheses, times 0.32, times answer squared. And we get that we lost 15.08 joules of kinetic energy. So here's another example. Merry-go-round with moment of inertia 210 kilogram meters per second. It's rotating with an angular velocity of 8.3 radians per second upward. So upward, right-hand rule. That means it is rotating around counterclockwise. Person of mass 65 kilograms jumps onto the north edge with a horizontal velocity of 3.5 meters per second east by 14 degrees south. person jumps on right here, and they're moving kind of that way, east by south, just before he lands. What is the angular velocity of the merry-go-round after the person lands? Ooh, well, this is a conservation of angular momentum. Probably we can say initial momentum equals final momentum. The merry-go-round, we're given the moment of inertia, which is handy, because then we don't have to worry about which formula we're going to use or anything like that. So we have the moment of inertia of the merry-go-round times the angular velocity of the merry-go-round. Okay, now the person, we know the angular velocity is r cross p, r crossed with the angular momentum. When we know that when we take a cross product, it's the tangential component of something that counts, and we already worked out that that's going to be the cross product is related to the sine of the angle between the lever arm and the momentum. So if the momentum is that way, our lever arm is this way, then the angle that's relevant is that, which is the complement of 14 degrees. So we can do sine of 66 degrees, or, as we know trig identities, we could do cosine of 14 degrees. I think of it in terms of the tangential component of the velocity, so I would tend to write m times tangential component of velocity, which is 3.5 cosine 14, times r, which I didn't tell you. How about that? We'll say it's 1.5 meters. Radius of merry-go-round is 1.5 meters. Okay. And that's equal to the final angular momentum, which is the total moment of inertia, which is 210, plus this person point mass times omega final. So you can use that and then go ahead and calculate the angular velocity of the combination. I'll leave you to punch that into your calculator if you feel so inclined. Here's another fun example. We've got a uniform rod with mass 5m, length L. So one end fixed to the ceiling and is initially at rest. So our rod now is hanging from the ceiling, and it's on a hinge of some kind, so it can rotate around that axis. Clay ball strikes the fixed end, or strikes 3L/4 from the fixed end. So here's the fixed end. Clay ball strikes it right there and sticks. It's the angular velocity of the combination after the collision. Well, initially, we know initial angular momentum equals final angular momentum. So we have clay ball, point mass, mvr. So it's mv, r is 3L/4. It's equal to final momentum, which is moment of inertia of the rod axis through the end. That's going to be 1/3 ml squared. So moment of inertia is 1/3 5m times L squared plus clay ball point mass. So that gives us m times 3L/4 squared. Mr squared is a point mass. And angular velocity combination final. Yep. And so then we can calculate what this is going to be. This gives us a 3/4 factor of L goes bye-bye. Got a 3/4 mv over here, and over here we have a 5/3 plus, I shouldn't cancel the squared because it's still 3/4 squared, which is 9/16, times ml omega final. Oh, that's not the nicest fraction. 5/3 plus 9/16. 107/48, lovely. 3/4 divided by that gives us 36/107. Math cancels out. 36v/107L equals omega final. How much energy is lost? We can calculate that. We've done that before. I'm not going to take the time to do that here, but you can follow the pattern that we did. in number 21. To what height above its initial position does the end of the rod swing? Now this is a good one. Once the clay is stuck there, remember what is conserved as the rod swings up. Well, that's going to be conservation of energy, of mechanical energy. So we can say that the kinetic energy that it has just after the collision is equal to the potential energy it has whenever it comes to a stop. So that kinetic energy we know is 1/2 times I, which we've already figured out. What was that? 5/3 plus 9/16 ml squared. That's from this, times omega final squared. That's the kinetic energy just after the clay ball hits. And that's equal to some kind of height. Now, the end of the rod. That's tricky. Okay. What height above the initial position does the end of the rod swing? Well, we've got to think and relate some things. Now, if the end of the rod swings up to some height, h, say, then the center of the rod, let's say h equals height of the end of the rod. Well, if that's the height of the end of the rod, then the rod itself, the kinetic or the potential energy of the rod will be mgh, but it's h of the center of mass of the rod. So that would be the height of the end of the rod divided by 2. Right? That's how much the center of mass would move up. And then the clay ball, how high would the clay ball go if the end of the rod goes up some amount? Well, distance 3/4 from there, so that's going to be 3/4, whatever height the end of the rod goes up. Ooh, that's confusing. But now we can calculate. L goes bye-bye, M goes bye-bye, and we've got a bunch of fractions that are not the nicest. So I'm going to use my calculator. We've got 0.5 times 5/3 plus 9/16 times 36/107 squared on the left side. On the right side, we're going to divide out. We've got 5/2 plus 3/4, which is less nasty. So well, that's lovely. 54/1391. And then what do we have? We've got a b squared and a g. Whew, hardcore. But anyway, the key thing here is that you've got conservation of angular momentum in the initial collision, then you've got conservation of energy as it swings upward.